To get started with Axiom, you go to mattpuchala.com, and then you go to download, enter your email, and boom, you have a Dropbox location where you can download this whole thing. If you go to the support installation guide, this will give you an idea of how to install everything, and it's really as easy as just dragging this over to your Houdini preferences. I'm on Windows, so for me that's in the Documents folder under the Houdini version. So as soon as you do that, all you do is reboot Houdini, and we have all of these Axiom nodes available. Under the License tab, you have the ability to enable trial mode, which I think does a watermark or maybe allows this for a certain number of days. I'm not really sure how the trial mode works, honestly, but for anyone that wants to try this out without buying it, then that's where you go to check that on. If we go to Learning, Documentation, and Sourcing, all we need to do is feed in fields with these names, and it'll take care of the rest. So if you want smoke, density, temperature, it's using the combination of temperature and fuel to create combustion in this example. So do keep that in mind. It's not using the sparse methodology with the flame field. So you have to do that, but that's basically all you do. So if we were to plug in density right here, turn this on, and there we go. We have density. Awesome. But it would be nice to control this a little bit better with some maybe disturbance, some temperature, and a really high level of dissipation so that this disappears quickly. I'm going to make a copy of that density noise and instead call it temperature. So there's temperature, and we don't want a lot of this. I mean, we'll keep this at 1 just so that it's a normalized range. But if we do that, offset this a little bit so that it's different from the density noise. Also rasterize it right here. So we'll say temperature. And then on the Axiom solver, we can say input maybe about half of 1 unit for temperature. So that gives us this sort of thing. Let's also go to our dissipation, set that to 0.5, and we have all of our microsolvers available right here. So with the turbulence, we can turn that up. The disturbance, there's 2 of them right there. We can find those settings right here with disturbance 1, disturbance 2. I think that the block size is good for right now. And the cutoff field is right now density. So what field should be used for the cutoff is defined right there. And the disturbance field will only affect fluids whose field value is less than this value. So let's actually affect quite a bit. Maybe any density value of 0.5 or less gets hit by this. Okay, likewise for that guy. Let's see what that did. So as we go forward, there we go. It looks like we have that sort of thing going on. And actually with the Axiom solver, you can't scrub left and right, unfortunately. So what I do is I set a file cache, and every time I want to see what this is doing, you have to, let's say, cache this out and then see that again on the cache file. So let's say that this is our Axiom density volume, or whatever you want to call that. Delete the channel, Control-Shift left mouse, and then 75 frames just for testing purposes. Okay, so we end up with this. And it's not looking so great. I don't like how everything just kind of moves up as one big chunk. It's not really what ends up happening with our reference. So instead of doing that, I think it's a good idea to alter our particle simulation a bit more, have it so that it rises the most at the center where this was initially hit, and then along the edges it just doesn't rise very much. It kind of hovers above the surface. And so what we can do is we can multiply velocity by the volume that we masked up here. Remember how we had the metaballs and that masked off how far away we were from the center? Well, we can use that again for multiplying against velocity down here. So if we go up here to where we originally sampled that volume, we can just copy this guy, go down, create a point wrangle near our velocity, or after that I should say, and plug that in up here. Better yet, let's actually make a separate one so that we can control the fall off with this ramp. Remember that ramp? If we go here to our volume slice, we can, again, control where that is. And it would be nice to do that separately for the velocity multiplication. So let's take the second input and plug that in, calling this our vel mask. And this guy will be our scatter density mask. Okay, now paste that code in because that's what we can use to read off these values. And unfortunately, the volume sample only works on float data. And we're trying to multiply this against vector data. So we need to actually break up our velocity into velocity x, velocity y, and velocity z. But that's not too bad. We could just say at v.x times equals vol sample, val, and we can just do that for y and z. So if we do that, say y and also z. And now as you can see, we've essentially enabled our velocity to exist primarily in the center. So if we go to our popnet and we simulate this out, we should see the particles flying much more faster around the areas that are centered. It's also not a bad idea to add a collision to these particles at this point as well. So let's go ahead and add a static object. We'll create an object merge, bring in our terrain. So that's going to be our merged or combined geo islands, colliz polys out. And I'm going to just make a null here. Say that this is our colliz polys. Within our static object, sop path, colliz polys. There we go. Merge that in. Double check the collision by going to our collisions tab, turning on collision guide, and setting the uniform divs to maybe about 125 or 150. Usually that's what works for me. We'll go with 150. Turn that off, display geometry. Now as we go forward, we should see these particles behaving nicely. There we go. Now we have that. And this is going to work much better for sourcing our density and bringing that through the Axiom solver. Let's see what that does. So this now gives us a general idea about what's happening right now. We did successfully taper off the height along the edges, but this isn't looking very good quite yet. So in the next video, let's improve the overall quality of the simulation. It's going in the right direction, but it just needs help in a few areas.